Good afternoon, everyone. Welcome to this webinar about seismic analysis of buildings in SCIA Engineer. My name is Stéphane Rossier. I'm Product Development Engineer at SCIA. And so I will do the presentation this afternoon. And my colleague, Marco De Biasio, will be answering your questions in the chat. So let's get started now. So just a few practicalities before we get started. Actually, for your information, everybody is muted now during the presentation, so you cannot talk to me during this presentation. You can nevertheless ask questions in the chat box, in the question box that is available for you in the webinar software. And this webinar will be recorded and will be available afterwards on YouTube in the SCIA channel. So you can watch it again at any time later on. Small summary of what we are going to look at this afternoon. First of all, modal analysis in general in SCIA Engineer, calculation of structural vibration frequencies and modes. A small explanation about the improved reduced system for modal analysis in SCIA Engineer, which is a unique feature of SCIA Engineer. A brief overview of alteration of stiffnesses and masses in SCIA Engineer using property modifiers. The seismic analysis itself using equivalent lateral forces method. The response spectrum method as well with modal superposition. Then a brief glimpse into various types of results that are specifically for seismic results output. Finally, a summary of the different steps and a brief overview of a couple of additional features that are available in SCIA Engineer for dynamic analysis. All right, so let's get then started with the presentation itself with the modal analysis part. First of all, let me show you the example we are going to work with. So I'm going to use this small building for the entire presentation. It's a small administrative building, 5 stories above ground, dimensions of 40 meters by 22 meters, so nothing particular. Most of the walls are reinforced concrete shear walls, and there are a few masonry walls here, the ones in red, as you can see here. Here to give an overview of distribution of the shear wall. So it's a fairly irregular system. There is just some asymmetry for the response in the Y direction, but for the rest, it's a pretty regular building. So the whole idea of the presentation, the whole idea of the workflow we are going to go through now is essentially starting off from a model that has been prepared for static analysis, for static design of the building. And we are going to go through the different steps that are necessary to adjust that model so that it can be used for seismic analysis. So first of all, first step in this workflow is the definition of the masses and the modal analysis. Any dynamic analysis in SCIA Engineer requires as a first step that a modal analysis is carried out. For this, we are going first to enable the dynamic analysis in the project. So I'm going here to the project settings and enabling the functionality for dynamic analysis, as well as directly here, seismic spectral analysis. So these are the basics here for our project. And second step now is the definition of the masses. Masses can be defined in various ways, can be defined manually or automatically. I'm going to go through first the automatic generation. I can create mass groups in a similar way as we have load cases, and each mass group can be simply linked to a mass group, to a load case, so that the corresponding masses can be generated. So I'm going to skip the self-weight because that one is actually taken into account automatically by the program in the modal analysis. But I'm going to create a mass group for the dead load, for the masses corresponding to the dead load actually, which I link to the corresponding load case and configured to have an automatic update. And I do the same for the live loads. Here, linking to the live load case. And again here, check the option to have an automatic update of the masses. That update will be carried out automatically during the seismic analysis, but I can also here trigger it manually so that I can check what is happening here, for instance, for this one, and I have an overview directly here of the masses corresponding to this mass group. So if I hide the rest of the model, here we have surface masses that have been generated on the model. I can check the values here. For instance, on the roof, I've got 300 kilograms per square meter corresponding to the static load that was applied on that slab. This is for the automatic generation of those masses. And I can also go here into the service for masses and check for each mass group what is available. Again, here I can trigger the generation. You see also the different types of masses that can be generated manually, the different types, mass in nodes, points mass on beams, etc., surface masses on 2D members, and so on. So that's going to be sufficient for our use case. Actually, we don't need to generate anything manually. We have really everything standard. The second thing I'm going to do is to create now a combination of mass groups. So similarly to load cases and mass and combinations of load cases, I can create combinations of mass groups and assign coefficients. So typically here I will have mass combination. I insert in there all the mass groups that are available and just can modify the coefficient. So typically we are going to have 100% of the dead load mass that is here assigned. And for the live load, there's going to be a reduction factor, can be something like 0.3, for instance, so that it's only a portion of that mass that is taken into account for modal analysis. There we are. So now the next step is obviously to run the modal analysis. So I can do it from here. So instead of linear analysis, I can here just simply select modal analysis and run the calculation. I'm going to here save some time and skip that step and directly jump to another file where I have already the calculation results available so that I can show directly the results for that type of calculation. So different things are available in the results for this part. Going to the result service, and the one thing I like to do first always in that kind of calculation is to have a look at the calculation protocol, because it gives a large quantity of interesting information about my model, about how it behaves dynamically, and if I have a sufficient number of modes also for the seismic analysis. So typically here what we get is a summary of all the masses that have been taken into account in the analysis, in the modal analysis, which allows you to check also if it roughly matches what you expected. And here you get a summary table of all the eigenmodes that have been computed with their frequency, and most importantly also here the modal mass ratio, which tells you what is the participation of each mode to the dynamic behavior. So here we see typically that the first two modes, unsurprisingly in such a nice regular structure, are the ones that we are mostly interested in for seismic analysis. So we have mode number 1, which is predominant in direction Y with about 55% of modal mass, and mode number 2, which is the same in direction X, about 54% here. We can also see at the bottom of the table, here I computed altogether 30 modes, that I have a total accumulated modal mass ratio of respectively about 60 and 73%. So as you know, 90% is necessary to have a satisfying output for the for seismic analysis using the response spectrum method. So clearly we are below the limit, and that is not sufficient for a modal analysis to be used for a response spectrum method. But we are going to come back to that aspect later on. And I'm going first now to give you an overview of other things So obviously other results that are available, typically mode shapes. So here I go simply into displacements and I can display the corresponding deformed shape for each mode. So let's take number 1 here, which was the mode in direction X, for instance. So there we are. We have a nice deformed shape in direction Y for mode number 1, as expected from the calculation protocol. Can also here, for instance, get an animation. There we go. Can also change the point of view directly in the animation and see what is happening. So we can see here that there is a nice combination of translation and torsion in that mode. And same here for displaying, for instance, the second mode, which was in X direction. You can see the shape here. And from the top view, you can see that it's perfectly symmetrical. There is absolutely no rotation on this one. So this is mostly what is, well, these are the key results basically from a modal analysis in itself. And we are not going to dig much deeper in this for now. I'm going now to continue next with the IRS analysis, as I had mentioned before. So let's go back to our PowerPoint now, because I want to show you first some bits of theoretical background about this, because it's a specialty. In typical modal analysis of building, you're going to have so-called global modes, which are the most interesting, mostly for the seismic analysis. These are the modes that are relevant really for what we are looking into. But they are also, because we are using a 3D model, typically that kind of stuff that can happen. We can have local modes and local perturbation. So those modes do exist, of course, in the structure. However, they are totally uninteresting for the seismic behavior. These are not the modes that are going to be relevant for designing the shear walls of a building, typically. So what about the improved reduced system for modal analysis? It's actually a matrix condensation technique that reduces the number of degrees of freedom of the model. Typically, actually, in our case, it's really reducing the model to 1 node per story. So, and which leaves us basically with 6 degrees of freedom for each story. Multiple benefits to that method. It eliminates obviously all the local modes. Since we don't have the degrees of freedom that can represent those local modes, well, they will simply not be present in the results. Thanks to that, we get a better convergence of the modal mass, especially on complex structures. So we are going to need less eigenmodes in order to achieve the 90% of modal mass ratio that is needed for completing a seismic analysis. And finally, again, thanks to the reduction of the size of the model and the number of degrees of freedom, it reduces the computation time. So also benefit on that side, we get faster our results. Configuring the IRS model in SCIA Engineer, that's very straightforward. Just need to define the stories and activate the IRS model in the solver settings in SCIA Engineer. What does it look like in the background? Actually, well, the model itself, you don't need to do anything about it. You just model your structure in 3D as usual. And that's our starting point for the reduced system. So from there, we actually use the mesh, the finite element mesh. In this simple case here, this is not the example we are using. Actually, ours is bigger than this, but this simple example has about 15,000 degrees of freedom with the original mesh. And using the matrix condensation technique, it's converted into, well, okay, it's not exactly this, actually. It's a bit more complex than that in the background, but think about it of a simple model like this one with just 1 mass per story and some connection between them. So really simple, really straightforward, typically the kind of model you would use for a hand calculation, actually. And this one has only, in this case, 24 degrees of freedom. It's about 600 times smaller than the original mesh. So big benefit on that side, obviously. And then after the modal analysis carried out on that reduced system, we extrapolate again using the inverted conversion matrices, and we obtain the results on the initial mesh. And again, so we obtain all the results. We have the displacements, the full model shapes, as well as internal forces and stresses in the model, which will be used then for the design. So this is the general principle. So again, initial structure, initial mesh, conversion to the reduced system, so drastic reduction of the number of degrees of freedom, modal analysis with that very simplified model, and finally extrapolation to the initial mesh to obtain the results that we need for the actual design. There we are. And now the results. So I'm not showing you the results. Well, no, sorry, actually. I'm going to show you briefly the settings for the IRS analysis, what needs doing. So as I said, the first step is to define the stories. In this case, it's already done. You all know the definition of stories in SCIA Engineer here, line grids and stories. And definition of stories. I have my stories that are defined here. In my case, 8 stories, simple repetitions, 2 times 4 meters for the 2 basement levels, and 5 times 3 meters 50 here for the above ground levels. So that's the first step. Here it's already defined. And second step, when I run the calculation, in the solver setup, in advanced solver settings, here, if I scroll down in the dynamic section, I need to check the option use IRS improved reduced system method. Just tick that one on and run the calculation. That's it. Straightforward. Just be aware, obviously, because of the nature of the model, of the analysis model, obviously your structure needs to fulfill certain requirements. For instance, it doesn't make sense to use the IRS method if you have multiple towers in the building, because there you wouldn't have sufficient degrees of freedom to represent correctly the behavior of the structure. But essentially, for, let's say, regular buildings, well, more or less regular buildings that are, let's say, designed in a reasonable way, that method is perfectly suitable. Typically, the method was actually designed for high-rise buildings, actually. So for a tower, perfectly fit, no problem. So going back to the results, actually. So here, actually, well, the results would be exactly the same as the types of results, sorry, would be exactly the same as what we get in a standard model analysis. However, there are a few differences. As I said, number of degrees of freedom changes drastically. In the standard model analysis, the finite element mesh would have over 100,000 degrees of freedom in this case, in the case of our building. The reduced system has only 48 degrees of freedom. So big reduction. Computation time, okay, not that bad, but still we're about half the computation time just for the modal analysis, down from 1 minute 30 to 43 seconds. So already quite a big step. Now imagine a model that would take normally, say, 20 minutes calculation. Well, here the gap would be even bigger, typically. Fundamental periods, well, those we would expect to get the same results, obviously, because otherwise it wouldn't make sense. So indeed, we get for both fundamental modes. I didn't list the rest, but you would also get similar results for the higher frequencies. You get typically the exact same fundamental periods. And also for the modal mass ratios, we get the same results, which shows us, well, okay, there is a tiny difference here, 54.2 and 54.3, so small approximation. However, shows us that the mode shapes are practically the same. So good sign again here, means that the IRS method does the job correctly. And finally, the cumulated modal mass ratio, so the total at the bottom of the table, we had only 60 and 73% in the original analysis with the full mesh. And now we are already up about 10%. We get 71 and 81% respectively in X and Y direction. Still not sufficient. It's still not sufficient because actually there are other things that need fixing in our model so that we get the 90% that we need. However, there's already an improvement because local modes have been eliminated from the calculation. So that is the general thing about the IRS analysis. Another thing, however, that I want to show you in the results is about some specific results that are already available now, thanks to the fact that we have the IRS analysis, and these are so-called Storey results in SCIA Engineer. These results are available only when stories are defined. There are detailed story results, which I will come back to later, actually, and more specifically, in this case, summary results. Summary results here give you detailed information about the reduced system. In this particular case, the one thing I want to show right now, I'm going to come back to all the rest later on, is the story data. So you can display here what we call story data. Actually, it gives you a nice summary of the masses per story of your model. So you have an overview of the simplified model here. So I can see my masses per story. I can also display that as a table. Here you go. So you get for each story the position of the mass center in global coordinates, as well as the total mass. Also, some components of the mass matrix actually for each story are provided. So different mass components as well as rotational components of the masses. There we are. So that would be it about the reduced system. Next step, alteration of the stiffnesses and masses. This is actually going to be one of the key points that need modifying. If I go back again to my model here and leave behind all my tools and result for the IRS analysis, which will remain active in the background. I'm not touching that. But essentially, two things. So alteration of the stiffness and masses, as I mentioned. For the alteration of stiffnesses, very well, a usual method would be to modify the E modulus typically of the materials, but we don't want to do that because it has also some other effects on the model. It would modify then the results in the checks because it would also modify the resistance of the materials, and so we don't want to do that. A much better way in SCIA Engineer is using what we call property modifiers, which allow to modify the stiffness of the members, typically for the analysis, but not touch the materials themselves. So I'm going to do that. I go back to my project settings and enable here in functionality what we call property modifiers. There we go. And now I'm going to actually modify the stiffness of all my shear walls. Why do I do that? Because actually there are well, one of the key things in seismic analysis is that you need to take into account the fact that shear walls, concrete shear walls in our case, are cracked, obviously, due to the seismic action, and that has an influence on their stiffness, which will affect also the fundamental period of the system, and therefore also the accelerations, the values that we read on the response spectrum, and so on. So big impact on there, potentially, and we want to take it into account. I'm going to modify the stiffness of the different walls, of the shear walls, of the concrete shear walls. Just a little thing before I do that. Actually, there are also those masonry walls that I haven't been talking much about until now. Let me hide the rest of the structure. Actually, we're interested now principally in walls. And we have those walls. So in red here, the 4 red walls, these are masonry walls, and those actually are already modeled in a particular way, namely that there are hinges everywhere, all over the place at the edges of my walls, also for concrete actually, but here in particular for shear, for the masonry walls, the sliding along the upper edge of those walls is already freed by hinges. So I have already, maybe you noticed when I showed the mode shapes, actually, I can show it again. Let me show here, and most interesting is mode number 2, which is in direction X. And you can see clearly here that my special hinges are acting there and that my masonry walls are nicely disconnected. They just slide on the top of each other. They don't get that typical bending deformation that my concrete shear walls have here. Here we really have a nice bend shape. And for the masonry walls, on the other hand, they just remain undeformed, but they just slide on the top. So I'm not going to do anything about those masonry walls. Actually, I'm just going to leave them alone because they are already behaving the way they are supposed to for seismic analysis. I'm going to just going to push them out of the way. I just hide them now, and we are going to take care of our concrete shear walls. So let's see. Now I have enabled my property modifiers in the project settings. I go to the structure service, and in model data here you have 2 new options: property modifiers 1D and 2D. 1D for 1D members, so columns, beams, etc. 2D for 2D members, plates, and walls. In our case, walls are the interesting part. So creating new property modifiers. There are various ways of using it. I'm using the simplest possible way here, just defining percentage of stiffness. There, my results are going down the drain, obviously, because I modified the model now. And I'm going to input an actual stiffness modifier value, say 30%, which means I'm keeping only 30% of the nominal values of the stiffness. Actual stiffness, this is really the in-plane behavior of my shear wall members that I'm interested in. Bending stiffness would be out of plane behavior. This is not what we want to touch, actually. Yeah, and let's call that, I'm going to use that for short walls. What do I call short walls, actually? I'm going to apply those property modifiers onto all my walls that are short. So that's typically, there are some, here, all the walls in the middle here, and there is another one here, and there's another one here. Let's see, did I select correctly? Apparently, yes. There, I applied my property modifiers on all my short walls. Now, let's say also that for the long walls here, the big walls of the basement, those ones are going to crack a bit too, but much less because they are much longer here, hence they have lower stress levels. So let me also create something here. I'm going to create a new set of properties for long walls. And for those, I'm going to take, say, 70% of the nominal value. There we go, long walls. And I'm applying this on all the walls of the basement. Here I'm selecting everything. It's just skipping the members for which there is already some settings, so I can't overwrite by mistake what I have already done. There we are. So I have my property modifiers applied now on all the members for my model. So that is for the stiffness of the members. That was one of the things actually that needed fixing in order to get proper behavior of my model. Second thing is the fact that we do have, let's call that irrelevant masses in our calculation at this point. Typically, we have a very rigid box in the basement here, so-called we could call that immobilized masses. And this is typically what is causing that problem with the modal mass ratio with the analysis. So a quite common practice would be to remove completely those masses from the analysis model and to really look at the dynamic behavior of whatever is above ground, actually, which is what I'm going to do here. So there are two things that I need to do. I need to filter it in two different ways. First of all, there is the mass related to the self-weight of the structure. This I can do again through the property modifiers. So let me see. I'm going to first go back to this and ground floor. No, this is not the one. Let me just keep displayed only everything that is at the ground level and below. There we are. So these are my 2 levels basement with all the shear walls and the 3 decks that are included in there. I'm also going to apply property modifiers on there. So I already actually have property modifiers on all the walls of those 2 levels, but I also want to modify the mass of all 3 slabs, the 3 decks, because honestly there is a lot of mass in there and they are not interesting for my dynamic behavior right now. So I'm going to create yet another set of stiffness, because for the slabs, I don't want to modify the stiffness. I want to keep my 100% there and applying them on all members. There we are. Okay, they are not sticking out so much, but here they are. 3 new nice labels on my 3 decks. And now that I have created this, I can select all my property modifiers. There we are. Property modifiers here. And you see that we have 2 coefficients here. I can modify the self-weight factor, which affects the static analysis, the self-weight load case actually. And we have the mass factor, which allows me to modify whatever is happening during the dynamic analysis for modal analysis. So I'm just going to set to 0 this part. And with that, I'm getting a nice 0, let's call that self mass in my basement levels. That was the first thing. Now, if I leave the structure service and display the entire structure again, let's get our model. There we go. You remember that we had generated masses from load cases. So if I go back here to my masses, these are the masses related to the dead load. And I want to remove whatever has come into those 3 lower decks. So for this, here in this case, simplest is that I disable the automatic update of masses and just delete those surface masses. There we go. And I repeat the operation for the other mass group. There we go. So now my model is clean and I have only masses above ground, basically. Last thing I can do still for the masses is in such a building, we actually don't need to calculate the vertical component of the size of the dynamic behavior of the structure. The vertical component could be simply taken into account as a static load case. It's more than good enough in such a case. So I'm going to disable completely also the vertical mass components for my modal analysis. This I can do very simply in the solver setup. Again, when I'm about to start the calculation and go into the advanced solver settings, in the dynamics section here, you have mass components in analysis, and you can here select which components you want to be taken into account. I can just uncheck the global Z component of the mass, and there we are. Then I can start the calculation for this. So again, I can start the calculation, but I'm going to save the time again and go directly to the results. This one here. So here we have the results actually with the with all the changes that I have done until now. And actually, I'm going to jump directly to my PowerPoint. Where is it? I lost my PowerPoint. Here. Yeah. So if we compare the results again now, that first column, these were the results I just showed before for the after the second modal analysis run with the IRS system. And now what do we get? Well, okay, number of degrees of freedom, computation time, essentially no change, which is normal. Fundamental periods are higher, which is normal because we have a system that is slightly more flexible thanks to the property modifiers that made our shear walls more flexible. So slightly higher values of fundamental periods for both X and Y directions. And most important, how here, modal mass ratios. For the fundamental modes, you see that we jumped from 54 to 80% and 75% here. So that's nice. And if I look at the cumulated values, we are, well, close to 100. This is actually because I kept the 30 modes I had originally computed. We would need less in reality in order to achieve what we need for the seismic analysis in our case. I will come back to that point later, actually. So this is about the modal analysis and the changes that we can do to the model to improve this. Next step. Let's have a look now at the actual seismic analysis, starting with equivalent lateral forces method. So quick introduction on this. Well, you're familiar with the equivalent lateral force method. That's obviously the most well-known method for that type of calculation with engineers. Requirements from the code, the structure must be regular in elevation, obviously, which means continuity of lateral load resisting system and the regular distribution of masses in the vertical direction. And also, there is condition in the Eurocode that says that the fundamental period must satisfy certain criteria. Okay, I'm not going to go into detail there. However, I'm going now to go in there and have a look at what we have for definition of the of the seismic load case in itself. So actually, I don't want to mess up this file. I'm going back to this one and just going to show you how those seismic load cases, those equivalent lateral forces, seismic load cases get created. First of all, well, obviously, creation of a load case. So let's call that earthquake X. That's going to be this. I need to create a separate load group. So this is a variable load case, obviously, variable action. But here, so as I said, new group for earthquake action. The type of load here is different. I'm going to select seismic here. It's a particular variation of the accidental loads, actually, and this one we want to have in this setting. And I'm going to select here together, which allows me typically to create afterwards the seismic combinations with combining the earthquake action in X and Y direction. Okay. Then second, load type. So that's no longer static, actually. That's something else, but I want to switch it first to dynamic for the seismic load case. And you see the default now is seismicity. And I have to first define my response spectrum. This is where my seismic action is going to come from, actually. So in direction X, I enable this. Seismic spectrum can be input manually or much simpler, actually. You're using, for instance, spectrum generator. I take the Eurocode here. Let's take period presentation and code parameters. So here I find all the settings that are typical for definition of the spectrum according to the Eurocode in our case. So let's change coefficient acceleration 0.1, for instance. Behavior factor, let's make it 2, and let's say subsoil C. Yeah, that will be sufficient for our purpose. So there we are. We have our nice response spectrum, which is defined. So I can create as many as I want actually here. And the next thing now is indeed to activate the equivalent lateral forces method. I'm going to come back to all the settings later on. First, I'm going to activate ELF method. There are 3 possible methods essentially here, which define how the accelerations are defined, how the accelerations are distributed across the stories of the building. Simplest method, linear distribution, which corresponds to what is typically done for hand calculation. Or second choice could be distribution of acceleration from an eigenshape. So there I would choose a mode shape and use that for distributing the accelerations. And last method here, polynomial. Actually, it's something that comes from the American ASCE code, so I'm not going to use this one right now. Let's select linear for this case, and well, you see that a lot of settings have disappeared actually because they are not necessary for ELF method. The only thing I need to do still is to activate here to choose which acceleration I want to use. I have 2 options, either max acceleration of spectrum, so taking the value of the plateau, or I can input manually the value here of the fundamental period. Let's say, so that was for X direction, and if I remember correctly, it was 0.66 second for the X direction. There we are. So that would be for for seismic action in direction X. I can make a copy of that for direction Y, and I'm just going to change the components here. So I untick X, enable direction Y, coefficient 1, and there we are. My seismic load case is defined in direction Y. I'm just going to change this one and use here, instead of linear, let's use the distribution from eigenshape. And I know that mode number 1 is actually the one that is that corresponds to behavior in the Y direction. So I'm just keeping that one. There we are. And the last thing I want to define is the accidental eccentricity. Accidental eccentricity, that actually needs considering like this. Eccentricity, there are 2 types of eccentricity actually to be taken into account. There is structural eccentricity. That actually, well, in hand calculation, you need to do a lot of fuss about it. In a 3D model, well, it's there. You actually can't remove it. So it's automatic in there. The accidental eccentricity, on the other hand, needs taken into account. And this one, well, there is a fairly simple method that is proposed also in Eurocode for this, which is essentially also an ELF method. We calculate torsional moment about the Z-axis, the global Z-axis, and apply them to each story. So this is how we're going to do it, basically. In SCIA Engineer, we just switch on here the accidental eccentricity method, and I select just, well, by default, it proposes only the same method as the one that was used for the ELF method. And you get here the eccentricity factor, so the typical 5% that you find in most seismic design codes. For the Y direction, I can enable it too, and here it's proposing only the mode shape because it's going to use the same as we defined here. You can see that 2 additional load cases have been created. These contain these equivalent moment related to the the accidental eccentricity for those 2 seismic load cases. Now, what do we get as results? Sorry, actually, one more thing before going to the results, the combinations. Creating the combinations for seismic action, well, actually, that's quite simple. Just going to delete that stuff and create a new combination for earthquake. Well, very simple. I select here, in my case, the Eurocode seismic combination. let's call that EQ again, and put all my load cases in there. So I don't need to do anything particular because if I use the Eurocode combination, the program knows automatically what is what and what coefficients need applying. If I check the content of the combination, what has been generated actually, content of combination, what we get is this. We have 3 combinations here. Well, okay, we have permanent loads alone. And here 2 combinations that follow the principle of Newmark as you have it defined in the Eurocode, with earthquake in direction X with coefficient 1 and direction Y with coefficient 0.3. And you see that the corresponding accidental eccentricity get the same coefficients. And the third one is the opposite with a predominant Y seismic action, basically with 1 and 0.3. So that's it. I don't need to do more. And then I can now look into my results for the seismic analysis. So let's have a look at what we have there with the results. Not going to go too much into detail because essentially we get similar results as for any static analysis. But just some overview. If I, for instance, look at deformed shape for, say, the EQX, so earthquake load case, the seismic load case in direction X, there we go. Unsurprisingly, something like that. Very similar to the mode shapes actually that we had looked at before. No distortion in the transverse direction. If I look at the Y load case, this is what we get here. And also I can look at what is happening, for instance, for one of my accidental eccentricity load case. There we go, pure rotation. One other nice thing you obtain from ELF load cases is that if you go back again to summary results, please note that ELF analysis is available only when the reduced system is as well enabled, because the simplified model, the reduced system, sorry, is used to calculate the distribution of the Storey forces to the Storey. What I can do here is for seismic load case also get a nice overview of the Storey forces, like in the, okay, these are the masses, but I can also have here Storey forces, for instance. So here are the ELF Storey forces that are applied at each story. Can get also again a summary here as text output. You get the summary table of everything at each story, the total values, the base shear essentially here. So 3,474 kilonewton for the total base shear, as well as a summary of the assumptions that have been made for the calculation of the load case. There we are. So that would be for ELF calculation. If I continue now, the next step, well, okay, that would be for the ELF calculation. Now let's have a look at what we can do if we want to do a response spectrum method with modal analysis. I'm going to modify now my seismic load case settings so that I can run a response spectrum analysis. First thing, here you can see that we have load type static equivalent, which is because we have our ELF calculation that is enabled. Well, the first thing I'm going to do is to disable ELF calculation. So ELF method here, I click on disable now. Again, we lose the results, obviously. And I'm again back to the definition of the load case, which allows me to define everything for the dynamic analysis in this case. What changes here? First of all, the modal superposition. Modal superposition, we are going to select here. I'm not going to use this RSS. I'm going to take CQC modal superposition with 5% damping. Let's do the same on Y. there we are. Then next thing is the mass in analysis. I see that I actually skipped some theoretical explanation there. So response spectrum method, you know all the typical conditions. We need to have the 90% mass of the total mass of the structure for the modes that are taken into account in the analysis, so that it can be considered sufficient. So that we have seen in the previous step of the modal analysis that we do have those 90% now with the reduced system and the correction of masses and stiffness that we applied. Modal mass in the analysis is one of those settings that actually allows to, let's call that, cheat on the modal mass ratio, because in case you are not achieving those 90%, there are some ways to actually compensate for it. So there are three options. Participating mass only will essentially, well, just use the modes that are there, that have been computed. So in this case, you really need to have more than 90% in the computed modes. Otherwise, your calculation is plain wrong, basically. Second option, missing mass in modes, allows you to simply amplify the results obtained from the calculated mode. So we apply some correction factor essentially on each mode shape so that it compensates the lack of modal mass ratio. It's not the best method, but it's already something that can be done to compensate for this. So say you have only 80% of modal mass, you apply the correction factor so that you reach the sufficient modal mass by that trick. And the last method is the residual mode, which consists essentially of making the assumption that the part of the mass of the structure does not vibrate because it's too stiff or for some reason, basically, and therefore it's subjected to the ground acceleration as a rigid body. So essentially, static forces are generated that correspond to that ground acceleration on those missing masses, and that's computed as an additional pseudo mode, which is computed and then included in modal superposition. In this, I can simply do it, for instance, if I do it for the Y load case here, I can say mass in analysis and select residual mode, for instance, as simple as that. Next step is the mode filtering. Mode filtering allows you to actually carry out the modal superposition only with the modes that are relevant for the calculation. So if you have too many or plenty of modes that give you a lot of information that you don't need, local modes or something like that, you can filter them out and use only the most significant modes. I'm going to that on both here, and simply here mode filtering enable with the total mass, and here I set my 90% essentially. So what does that mean? It's going to use the all most significant modes of my modal analysis until we reach 90%. All the rest we just leave out. It's not necessary to obtain the results. Finally, last but not least, the signed results. Because of the modal superposition technique, obviously, we obtain results without their sign. And this is not so convenient for design because you lose concomitance of the results and it's getting tricky to perform the actual design. So what does it do actually? How does it work? Principle is fairly simple. The modal superposition gives us some value without a sign. So it can be CQC or SRSS method, doesn't matter. Then we consider the predominant mode, which is the one that gives the most contribution. And then we combine. We take the value from here, the sign from here, and we obtain a nice signed envelope. So this is what we are going to do here in our case. And the typical results that you get is, well, without the signature, you would get that kind of stuff. And here you can imagine if you need to compute a resultant force from stresses that look like that, well, you get nothing usable. After signature, it's obviously much easier to read also for the interpretation, for the simple interpretation of the results, much more convenient like that. So what we do here in the load case settings, we enable predominant mode. And for the X direction, we know that it was mode number 2. And for the Y direction, it was mode number 1. So did I do that right? 2, 1, yes. Okay, so there we are. We have all our load or seismic load cases that are defined. I don't need to touch anything to the to the combinations. The rest is completely okay. Now, if I go into the results, so hang on, that's going to be this one. Yep. So there is a bunch of results now that are available. I'm going to focus on the stuff that is specific again. First of all, again, the calculation protocol, which gives a nice overview. I'm looking now no longer at the mode shape calculation protocol, but the linear calculation protocol, which gives, as you well know, summary for all the static load cases, and also for each seismic load case, a summary table. Here I see the result of the of the mode filtering. Also, you see that I don't get 30, but only 2 and 3 modes, respectively. So really few that are sufficient to reach over 90% of modal mass. Huh? So what do we get on that actually? So this is one of those tables. We have obviously a list of all the different modes that have been used for each load case for the modal superposition. We get some reminder of the natural frequencies. We get a reminder of the modal mass ratio, very important, in the direction of the seismic action. Not any, just really in the direction of the seismic action. With the total at the bottom, I can check here. Yes, I'm above 90% with those 3 modes here. That's good. Spectral acceleration values are also listed here corresponding to each mode. And here I guess my seismic forces base shear in this case for each mode and for the modal superposition, and also overturning moments relative to the reference level that is also shown here. In my case, 0. That's what I kept in my seismic load case settings. And finally here, so the first 3 lines in this case, well, these are the eigenmodes. These are the first, the 3 filtered eigenmodes that actually are used for modal superposition. Next line, this is the residual pseudo mode. You remember that for load case in Y direction, I enabled the residual mode calculation. Well, it's here. That's that pseudo mode that is used also to take into account the little bit of mass that is missing in modal superposition. Would have not been necessary in this case, but okay, it's just an illustration. And finally, at the bottom in the last line, the modal superposition results for this seismic load case. There we are. And results now. I see that time is flying. I'm going to try to go quickly on the rest. So let me see results. One first thing, the summary story results. I already showed that actually in a number of things, in a number of places for the IRS analysis. We get a few more things here again, which I didn't show before, typically for a seismic load case. And seismic load cases only in this case, it's really all the stuff that comes directly from the IRS analysis. I can, for instance, display displacements for the seismic load case, EQX X direction, yes. So there you are. You can obtain the displacement at the mass center of each story. So typically all the results are presented at the mass center in this case. I can have displacements, inter-story drift, accelerations, and so on for each story directly here. So really nice summary results in this case. So that would be for the summary story results. Detailed story results give you the possibility to display also values in all supporting members. In this case, for instance, if I take, well, let's say again, earthquake in direction X, and let's filter that, not all stories, but I'm going to take just the ground floor, which is here. This one, that's going to be 1, 2, 3, yeah, FL3. So for instance, here, I can get internal forces in both, I display it like this, in both the walls and the columns directly on one drawing. Okay, that's global extreme. Let's take per member. There we are. So I can here, for instance, see for my core in the middle directly vertical forces intensity, and on the same drawing here directly for the different columns, I guess normal force and so on. So you get a nice summary of this. This works also, by the way, for any load case. I can do the same for self-weight load case, for instance, and get values directly for the entire story. I can also get resulting forces per member. Let's take that's going to be Fy. There we go. No, that's not Fy that I wanted, but that's going to be suitable for my seismic load case. There we go. We have the shear force for each member here in my for my seismic load case for each of the shear walls of the structure in one go. And finally, what I can also get is resulting forces per story this time. So that's going to be the resulting force for all, well, for one story or for each story separately. If I display just one here, that's for the ground floor again, but I can also display it like this and select here all stories. There we go. And here I get essentially the total shear force combined for all shear walls, sorry, not shear walls, for all the walls, actually, all the supporting members of the stories. Again, you can use that for static load cases, seismic load cases, whatever, or for combinations. It works exactly the same. So you can do some kind of load descending representation for your building also using this. That's no problem. And the last thing I want to show you for the results is here the integration members, which is something that came out last year, if I'm not mistaken, which is a very powerful feature to be used essentially, most especially for seismic calculations. So say, for instance, that I would like to have the results in a wall here. Let's take that shear wall that is here just at the corner, this one, and we would like to see what is happening in it across the whole height. So I'm going to create an integration member, rectangle center of gravity here, and just increasing number of points. There we go. And I can just draw it here on my model from here to the top. Now, what is that blue volume? That's actually the volume that it's a bounding box that will define which parts of the structure will be integrated. In this case, I want to make that a bit bigger. Say here 350, 350, there. And I have now that integration member that is defined. What do I do with it? Now, basically, if I select it, I can now output results from those 2D elements as if it would be a beam. So I go to internal forces in beams for my selected 1D member. I'm going to select load case, earthquake direction X, and we are interested, most importantly, let's take the bending moment. There we go. And I have directly here results as if that wall would have been modeled as a beam directly. I can also display the shear force here, or the normal force, and so on. So you have access to all the results in that selection of 2D members as if it would be a beam. Works for one member, works also for a group of members. If I want to see, for instance, what's happening here in the core, in the middle, same idea. I can create an integration member here all the way from the bottom like this. Don't even have to put it in the middle, actually. Let me see. So I'm gonna need a bit more here, and let's see the settings here. So left. And like this. So something like that. So I get my bounding box that encloses the entire the entire core here. And again, I can display results. I go back to my internal forces in 1D members, seismic EQX and MY again. There we go. And I get my diagram here, forces. Obviously, we have the peak here at the ground level, and then it decreases again in the basement. So you can nicely use that for the entire, for any group of members. Can also combine 1D and 2D members. It works in all cases. I could even create actually an integration member that encloses the entire building. Why not? That's also possible. And you can also display results if you wish. For instance, for the same member, I can also use deformations and display, for instance, average deformations in this case instead of integration of stresses. Direction UX, I'm not sure my settings. Let's see. Sorry, my mistake. Type of selections here. There we go. Okay, there is a peak at the top because the connection of the top of the roof actually is not perfect. There are some, you remember, there is the sliding aspect of the masonry walls, and that creates a slight discontinuity. There are less walls actually connecting less shear walls connecting the top slab. So that explains that little jump here. But you can essentially obtain also average displacement values throughout a number of elements in this way. So I'm more or less through now the list of all the features that I wanted to show. Let's have a look at our little summary. So we had a look essentially at, first of all, the modal analysis. So definition and generation of masses, mass combinations, modification of stiffnesses and mass corrections, and also, most importantly, the IRS analysis model. This is prerequisite, as I said, for any dynamic analysis in SCIA Engineer. You really need to have it, to have that done regardless of the type of dynamic analysis. Obviously, seismic analysis is one of them. And then the seismic load cases. In all cases, obviously, create a response spectrum. That's the basis. Can carry out an ELF calculation in this case. Note that IRS calculation is required because the Storey information is used to calculate the Storey forces in this case. That's the reason why. Or you go for a typical standard response spectrum analysis with modal superposition, define modal superposition method, mass in analysis, mode filtering settings, sign results, and so on. Finally, accidental eccentricity can be defined in both cases. It's calculated exactly in the same way, actually, regardless of the type of seismic analysis you choose. And in all cases, you need, again, the IRS calculation for the accidental eccentricity to be carried out correctly. Finally, definition of seismic load case combinations. And that's it for the analysis itself. For the results, very brief summary. We looked at summary Storey results, which are essentially showing results at the mass center based on the IRS analysis only. We have seen detailed Storey results, which fundamentally provide results in all the supporting members of each story. can be internal forces or resulting forces per member or per story. And that works for any load case combination, even for nonlinear analysis, you can use them, no problem. And finally, integration members, probably one of the most interesting features there, which allows you to output results from any group of members in a 3D model as if it would have been modeled as a beam, basically. It can output resultant forces or average displacements in that group of beam. There we are for this. So that's the thing for the summary about that presentation. And just a little bonus now. What else about dynamic analysis in SCIA Engineer? A couple of things just want to mention. For instance, we have possibilities for harmonic loading. So typically what is harmonic loading is just input of some loads defined as forces applied on the structure that have a harmonic behavior. So sine function typically with a frequency and some damping settings, some damping properties. What you get as a result from that type of analysis is typically just an envelope of results for the steady state response of the structure, displacement, internal forces, etc. You name it. Typical application examples for this, machine-induced vibrations, human-induced vibrations such as footfall analysis, although here, depending on the countries, obviously this is far too basic to fulfill the requirements, but there are nevertheless many cases where this is sufficient to use. And I came across some design codes where just one mode is sufficient actually to carry out perfectly valid analysis. Also wind-induced vibrations like Kalman vortex sheddings, for instance, is also available in the software. And another thing, dynamic time history analysis. So in this case, the actions, well, are not harmonic. They can be completely arbitrary. So just an example here. And in that case, what you get is not only the envelope of results, but really the full trace of all the results, internal forces, stresses, displacements, etc. in any point of the structure can be obtained, and you don't need to just have the envelope in this case. Application examples, so typically transient motion analysis, if you have some loads that varies bizarrely in time and you want to get the response, to obtain accelerations from moving loads, for instance, or blast loading, impact loading on a structure, and so on. You name it. There we are. So that would be more or less it. Next, your questions. But actually, as I see on my screen, it looks like most questions have been answered already. So fortunately, since we are already far beyond the time that that we had planned, I think we are going to drop it here. But if there are any questions remaining, we are going to answer them by email. So don't worry, you will get answers to your questions regardless. Well, that's it basically. So thank you very much for your attention. If just at the end of this webinar, you could just take a couple of minutes to complete the survey that will be displayed when you leave the webinar, that would be great. We would really be grateful. That would be also, that would give some nice information for us to continue our work. And that's it from my side. So I wish you all a very nice end of day and continuation. So goodbye.